the right-hand side part of the formation dipped down. So this, at the time, it was normal stress regime. How about this one? If you look at it, and you look at it from far away, you can see as if the formation just slipped sideways. That's a strike slip situation. How about this? You see the fault here, and rock actually bent as if it is as if it's a soft thing, but under high pressure and high temperature, even rock will turn around. That's the reason we see an anticline and all this geologic formations. So this is, you can see this right-hand side dropped below this right side, that the left-hand side part of the rock. That is reverse faulting. So this must have been, at the time it happened, must have been extremely deep. And not only deep, that's high pressure and high temperature, but also was exposed to some external, very high external forces that caused the horizontal stresses to be higher than the vertical stresses. We'll see why. So what causes all those stresses? We'll go through some of them, not all of them. The biggest one is the tectonic plates. Let us look at it. Then we'll talk about topography, the mountains, lateral variation of the thickness of Earth, sometimes localized load, and it may be just the weight of the rock. Thermal stresses can be important also. We sometimes take advantage of this in the fracturing process. I will talk about it a little bit. So, tectonic plates. If I look at this map, and this map was created, as you can see at the bottom here, by Karlsruhe University. You know, when I hear that, it's like this because I spent one summer actually as a graduate student at Karlsruhe University of Karlsruhe. It's an interesting place, very strong technically. You look and you find the Earth is broken into pieces. You look at this, for example, you look at Africa is sitting on a tectonic plate that looks very much like Africa, only part of it is above water, the rest is underwater. South America is similar, and North America is similar. Asia, Euro-Asia, it is in one tectonic plate. Actually, you can break the tectonic plates into, there is major ones, but you can break it into sub-major ones. I can tell you here in United States, you have this tectonic plates here, and it can cause earthquakes, and that's the reason for behind the earthquake in San Francisco back in 1905. Your tectonic plates here, you can see breaking through Iceland. We'll look at this in a second. So Earth is alive. Actually, people did not realize that there is such a thing as tectonic plates until the early 20th century. Someone wrote a paper on the subject, and people did not believe him. Because they thought it's just a coincidence that Africa and North and South America look the way they look. Till after Second World War, the exploration of bottom of the ocean revealed that there's actually this like a volcano type line here, and it was in this area. If you see around Indonesia, this is what caused the tsunami back in 2000 something, 2005, maybe around that time. But there was a huge tsunami that killed 250,000 people. And it was caused because of the tectonic plates, because tectonic plates, they keep moving. For example, the movement here across Iceland, basically the Euro-Asian plate and the North American plate, they go away from one another about an inch per year. It sounds like it's very small amount, it's a very small number, but over millions of years, that becomes a huge distance. So here, what they did in Karlsruhe, they were trying to find stresses. So, for example, an area like here, South Africa, this is thick arrows. This is an indication of a strike-slip situation when you have arrows going into one another like that. If they are going away from one another like this red arrows, that tells me I have normal stresses. I usually give students a homework to go download another map of your area. In US, I ask them to download the map for United States and explain what the stresses that we have. Those are regional stresses. Does not mean that local stresses will be exactly the same. That is, we already found that long time ago that this is not the case in South Texas, although it looks like you have some strike slip here, where many areas were actually normal stress, and the stress orientation changed across a fault. Okay, let's look. This is just showing part of the Alps is actually is from Africa, because you have the African plate and European Euro-Asian plate are colliding, and the African plate is basically going on top of the Euro-Asian plate. That causes a lot of stresses. If you go back to this map and you see these huge stresses near the Himalayas, near any time you have a mountain. In Iceland, I downloaded this map from Google. You can see in one side, this is Europe, on the other side, this is North America. And so there is a bridge that you will be, you go from one side to another, you are crossing from the Euro-Asian plate to North American plate. And this distance keeps increasing. So in lifetime of a person, it goes away by 6 feet. The way it happens, and that's the reason behind the tsunami, is one tectonic plate may be going under the other or getting separated. And what happened in the tsunami is, although we say it moved about 1 inch per year, does not mean it is going very smoothly. In the tsunami, there was no movement for a long time. And then it jumped, built up very high stress, and basically one plate jumped over the other. It moved the estimation is 25 feet. It moved the water, although it may not. If you're sitting in the top of the water here in a boat, you don't really feel it very much. But as it comes closer to the shore, it goes from inches into many feet, and so it has catastrophic effect, and that's what it causes a lot of stress. Another, the thinning of Earth, basically the lithosphere. You look at, I have to give you an example of the Gulf of Mexico is getting thinner and thinner, so the stresses change. So you find that your minimum stress, if you are here near New Orleans, your minimum stress is like this, and your fracture is perpendicular to it. If you are in Mexico, the minimum stress in different direction and the fracture is perpendicular to it. So does not mean that in the Gulf the orientation is the same everywhere. So that is one reason people will have to test the formation to tell the orientation of stresses and magnitude of stresses. We'll talk about ways to do that next week. Localized loads like salt domes. So you have salt domes. Salt domes is under the high pressure and temperature, it flows. Salt will, although it may be hard when you take it to the surface, but on downhole it flows. The same thing with chalk. You know, we have fractured the chalk formation, and if you look at chalk in the surface, when you take a sample, the surface is very hard, but downhole is flows like, not exactly like fluid, but it creeps very much. So salt dome, it moves and it can cause stresses. So I don't have a graph for it, but if you go downhole, if you take a cross section, you can see it's pushing the formation up, and the oil will be trapped between the salt dome and the formation, because salt dome has basically zero permeability. So you drill on the side of the salt dome. So as you move around, the orientation of fractures will change because orientation of stresses will change. Gravitational stress is interesting. You basically, it is weight of the rock. So your vertical stress in most cases, it is nothing but the weight of the rock. So it is, if I have various formation between surface and downhole, all you're doing is you're integrating that weight. So it is an easy equation to do this integration. If it is, you can break it into various layers and add the stresses. If you do not know the value, most people will say, okay, what is my specific gravity of sandstone? If you remember, if you multiply the specific gravity by 0.433, you get your gradient. And so that gradient for sandstone is about 1 to 1.1 psi per foot. And so if I do not know anything about the formation, I'm just making a very quick estimate. I would say, okay, my formation is 5,000 feet deep, multiplied by 1 psi or 1.1 psi per foot. Then my vertical stress should be between 5,000 to 5,500 psi. So that is an easy way to do it. If I give you a formation and said, okay, we have all this formation, here is the specific gravity of each rock. Some of them may be 3.6, maybe less, multiplied by 0.433. So if it is sandstone, is 2.65 approximately. So 2.65 times 0.433 is about 1.1 psi per foot or so. But if I give you information, you need to do it correctly. You can do it easily, and that's what exactly what log would do when they calculate stress for you. All they are doing is calculating the vertical stress. We'll talk in a minute about calculating the horizontal stress. So you're integrating. If I'm in water, then part of it is water. You can see the equation. Part of it is in water, part of it in the rock. So in water, the specific gravity is 1 times 0.433. So I have 0.433 psi per foot. So if I'm drilling in offshore well and water depth is let's say 2,500 feet, which is not really that deep in what we do now. So that will be 2,500 times 0.433. So That's almost 1,000 psi, or a little higher than 1,000 psi, and plus the weight of the rock. So let's look at the mechanical properties, the Young's modulus and Poisson's ratio, and Bart's constant. So we'll do it experimentally, like what we have done that personally. We've done that in the lab many times, and we do it also from logs. So if I do it in the lab, and there is a difference between the two, and the difference is kind of important. If I do it in the lab, you know, I get a plug or a core, and apply stress. I keep varying that stress, the force. I increase the force, so I'm increasing the stress, and I build. Then I take the change in height of that plug and divide it by the total length. That gives me the stress. So delta L over L is the strain. The force divided by the area is my stress, and draw this straight line, and the slope of the straight line is my Young's modulus. Okay, Young's modulus for a hard sandstone maybe 5, 6, 7 million psi. This is the stress is in psi. The strain is unitless, is dimensionless parameter because it's length divided by length. So if I have hard sandstone, maybe 5, 6 million, we'll give you a table later on about the values. So 5, 6 million psi. If you work in industry, most people do say 5 or 6, meaning 5 or 6 million, not just the 5 or 6, but so 5, 6 million psi, and I'm talking in English units. If you work with metric units, then you need to translate that. And the stiffer the rock is, the higher the slope. So if I go into softer rock, you get smaller. The slope is smaller, so it's smaller Young's modulus. Okay. Now Poisson's ratio. Let's talk about Poisson's ratio. Then we'll give a table. If I repeat the same, if I'm running this experiment again, and I'm applying this force, not only I'm measuring the change in strain, I'm getting, this rock is getting wider. So there is axial strain, which is delta L over L, but there's also lateral strain, which is the change in radius divided by radius, or you can call it change of diameter divided by diameter. And if I take the ratio of the lateral strain divided by the axial strain, that gives me what we call Poisson's ratio. Poisson was famous mathematician, French mathematician back in many years ago, in 1700s or so. You can see this. That ratio has to be less than 0.5 for a rock. If you're running these experiments on a rock, that ratio, that Poisson's ratio, is definitely less than 0.5. If I give you a problem, and I've done that before, trick the students. If I give you a problem and you end up calculating Poisson's ratio 0.5 or larger, unless I wrote the problem wrong, which is very unlikely, or you made a mistake, which is probably the case. It happened in an exam that I've given. And so I had to tell the students, hey, you calculate a value 0.5 or higher for Poisson's ratio, you are making a mistake. You need to look back into it. And why is that? 0.5 means that the rock cannot carry any load. So it's almost like fluid, like liquid. So obviously that is not the case. And I used to give a problem for students to understand that better. Okay. Then you have shear modulus. Shear modulus is basically the formation. If you apply force, and then your shear force, then it will deform the rock by an angle theta. And shear stress, shear modulus would be shear stress divided by this angle in radians, not in degrees. And you know the pi is basically 180 degrees. Okay, but you can calculate shear modulus. It is related to Young's modulus and Poisson's ratio. So if you know Young's modulus and Poisson's ratio, you can calculate shear modulus. It's interesting that they are all things are related to one another. Young's modulus and Poisson's ratio are independent variables. I'm falling behind very much, but so it's probably another half an hour or so. Bulk modulus is actually the inverse of compressibility. So if I apply stress around the rock, the volume gets smaller. So it is essentially 1 over compressibility, except that we call it, in rocks you call it bulk modulus. And again, its bulk modulus is related to Young's modulus and Poisson's ratio. So here is the relationship between one and the other in this table. That's assuming isotropic material. The values you have, you can see Young's modulus for granite, it can be 10 million, and this all in psi. In shale, it may be shale. You can have soft shale and hard shale. Most shales are not as hard. This is here we're talking about hard shale that is almost as high as rock, but steel would be 20 to 30 million. Cold seam is 0.3 million. Let's look at sandstone. Sandstone can get higher than 4 million. With Poisson's ratio, it's usually higher than 0, but Poisson's ratio has to be less than 0.5. Usually, in what we deal with, the confining shale usually is softer than sandstone. And this is a very interesting parameter. We are going to look at it in a minute. But let me first talk about the parameters we looked at so far: Young's modulus and Poisson's ratio, shear modulus. This we call them static measurements. Dynamic measurements is where you are vibrating the grains. So you want to vibrate the grains. What you do is you apply sonic wave. Sonic wave will vibrate the grains, and your vibration happens either longitudinal, as you can see in this picture, or transverse. So if you are in one place, and you can see the reference of this slide. And I find it like an interesting slide. And so you can see there is vibration going longitudinal or transverse. So if I apply sonic wave, the wave either will go compressional wave, so it moves from one place to another. So if I have a source in one, say at the bottom of the well, and I have a receiver a little higher, I can hear the compressional wave coming in, and then I hear the shear wave coming after it. Okay, and so I hear the compressional, then I hear the shear wave. The difference, the difference in time or in velocity of the two is an indication of Poisson's ratio. So here, if I'm listening to it, I take DTS, which is shear divided by compressional. This is taking longer time to arrive than the compressional wave. The shear wave taking longer time to arrive. I divide them one another, square it, take 1/2 minus 1 and do this, use this equation. I can calculate Poisson's ratio. And that's the way logs actually calculate Poisson's ratio. And then in a minute we'll see how you calculate the stress out of that. Because you run sonic log, you're getting density of the rock, so you can calculate the vertical stress. If you integrate the whole thing, you get the vertical stress. If I'm also doing sonic log and I have to have enough distance between the transmission and the receiver in order to be able to see the compressional and shear wave distinctly from one another. Once I get the Poisson's ratio, then I can get shear modulus. Here is a simple equation where A is a constant here, and from there I can calculate Young's modulus, and you will be in business. So you can do it. You can do it with logs, okay? Or if you have velocity, and here is the shear wave and the compressional wave, the V sub P. So before we leave this area, okay, let's say I calculated Young's modulus and Poisson's ratio here.